Hi, I'm Tim, and I'll be presenting our paper Self-Supervised Localization Between Range Sensors and Overhead Imagery. Public maps are ubiquitous nowadays. Got lost in a foreign city? Just choose a map service from your phone and navigate around. So why can't we do the same with robots? Overhead imagery such as Google satellite images are readily available almost everywhere in the world. We investigate how they can be utilized for localization together with onboard range sensors. LiDAR is a well-studied range sensor. Scanning FMCW radar is an emerging sensor. Its long sensing range, immunity to adverse weather, and complex interaction with the scene make for an interesting and promising technology for state estimation. In some forms of cross-modality registration, such as registering our LiDAR scan onto a radar scan, the two data domains are somewhat similar in nature. Other forms, such as registering range sensor scans onto overhead imagery, are highly challenging but enable many exciting applications. For example, localizing a radar or LiDAR is no longer limited to using prior radar or LiDAR maps. Public overhead imagery can now act as a map to localize against. We show not only is this possible, it can be learned in a self-supervised fashion without ground truth pose. This task is challenging for several reasons. The two images to be registered have drastically different appearances, therefore it's not clear how to establish data association. Overhead images capture a holistic top-down view of the environment, while range sensor scans are sparse and have a limited field of view. Ephemeral objects such as cars may appear in the overhead imagery but not in the range sensor data, and vice versa. Finally, due to its sensing nature, radar data comes with ghost reflections, which are not present in the overhead imagery. We decouple rotation from translation and solve the two sequentially. In particular, we seek to generate a synthetic range sensor image pixel-wise aligned with the overhead image. To infer the rotation offset, we use an architecture where given two images of different modalities, one of them is rotated many times with small increments. The output is a softmax from the rotation stack where the heading matches the other image. To achieve self-supervision, the key inset is to pass through the network twice, the first time rotating the range sensor image and the second time rotating the overhead image while taking the output of the first pass as input. By enforcing the output of the second pass to be the original non-rotated overhead image, we can ensure the first pass produces a range sensor image rotation aligned with the overhead image. The softmax output becomes more crisp as the network gets trained. Our insight to solving image generation is to use an encoder-decoder architecture where appearance and pose are disentangled. We first learn to separately encode the appearance of a range sensor image and the relative translation between two identical but shifted range sensor images. To do so, we generate a synthetic image with the encoded appearance applied with the encoded translation. The problem then boils down to learning a cross-modality pose encoder between an overhead image and a range sensor image. This produces a synthetic image pixel-wise aligned with the overhead image. The key is, if a known translation is applied to the input overhead image, the same translation will apply on the output synthetic image. This offers a consistency to establish self-supervision using modules learned from the first stage. Please refer to our paper for details. The synthetic images become more realistic with more training. We achieved results on par with the prior supervised approach on a large number of datasets. Here we show the estimated and ground truth trajectories in an experiment where the vehicle continuously tracks its pose for over a kilometer by localizing LiDAR against satellite imagery.